SwayamPrabha. Digital India. Educated India.
In dimensional form, we can write u del x equal to minus 1 by rho del p del x. If we integrate it, we'll get p plus half rho u square equal to constant. What is this? This is Bernoulli's equation, which is valid outside the boundary layer between any 2 points. Now, if it is inviscid irrotational flow, obviously between any 2 points. Boundary conditions: y equal to 0, u equal to 0, v equal to 0, or at y star equal to 0, u star equal to 0, v star equal to 0. At y equal to delta, u is u infinity. In terms of non-dimensional variable, at y star equal to epsilon, u star equal to 1. Outside the boundary layer, u star equal to 1. Non-dimensional velocity. Now, from here, we can attempt to derive thermal boundary layer equation. In order to derive thermal boundary layer equation, we have to first take help from definition of Prandtl number. Prandtl number is given by mu Cp by K. We can rearrange it as mu by rho into rho Cp by K, or mu by alpha. That means kinematic viscosity divided by thermal diffusivity. And this is of the order of velocity boundary layer thickness by thermal boundary layer thickness. So, energy equation, when we non-dimensionalize, we have already seen it and we have worked with it, non-dimensional parameters. So, for 2D, now we can write u star del theta del x star plus v star del theta del y star equal to 1 by Reynolds number into Prandtl number, del 2 theta del x star 2 plus del 2 theta del y star 2. And order of magnitude analysis, u star is of the order of 1, theta of the order of 1. We have seen maximum value of theta can be 1, minimum can be 0. X star order of 1, v star order of epsilon, del theta order of 1, del y star order of epsilon. And del theta del x2 again 1 by 1, del theta del y2 1 by epsilon square. And here this order we have to assign. We have retained the order of Reynolds number. Usually the Prandtl number for all working fluids, it is such that it doesn't change this order of magnitude value of 1 by Reynolds number. Why I am saying so? That Prandtl number varies in a wide range, 0.01 liquid metals to a value 1000. Now, for higher value of Prandtl number, this order will not change. For value of Prandtl number of the order, Prandtl number in the range of 1, 0.6, 0.7, 5, 6, 7, 10, basically, 1 and greater than 1 is not a problem. Less than 1 is a problem, but less than 1 usually for most of the gases the value is like air, it is around 0.6. Now, so basically or 0.72, very precisely. It ranges from basically, 0.6 to 0.72, 73, something like that, depending on temperature. Usually value is, what is used is 0.7 and 0.6 is not correct, 0.7. So for all those values will not change 1 by Reynolds number order. What will change is very small value, which are the values of basically Prandtl number of liquid metals. Now we can sort of exclude liquid metal from our analysis. So for all other fluids, we can say that 1 by Reynolds number into Prandtl number is of the order of epsilon square. Then again, if we want to retain order of 1 on both the sides, we'll be able to write U star del theta del x star plus V star del theta del y star equal to 1 by Reynolds number into Prandtl number del 2 theta del y star 2. Non-dimensional value. Dimensional value, if we go back from here, we will get rho Cp U del T del x V del T del y equal to K del 2T del y2. Physical significance is basically del T del x is not to be dropped as it is 0 on that argument. It's to be dropped because del T del y is much greater than del T del x. That is, axial conduction in fluids is much less than that of the diffusion rate. That means the cross diffusion in the normal direction. So axial conduction in fluids much less than that of the transport or diffusion rate in the normal direction. Please note that del T del x cannot be 0 because if the heat transfer is taking place, del T del x will change as long as heat transfer is taking place. However, del T del y is much greater than del T del x. So Nusselt number, we can say that dimensionless temperature gradient at the surface, it becomes a function of U star, V star, X star, Y star, theta, Reynolds number and Prandtl number for forced convection in the absence of dissipation and volumetric heat generation. This can also be shown that non-dimensional form of thermal boundary layer equation becomes U star del theta del x star plus V star del theta del y star equal to 1 by Reynolds number into Prandtl number del 2 theta del y star 2 plus Eckert number by Reynolds number into 2 into del U star del y star square. This is the highest term in the viscous dissipation function, del U del y gradient if it is significant. So we have in the entire viscous dissipation function, we have only retained this term. This is in presence of viscous dissipation and subsequent. So this is the equation. As we said, this can be shown that the non-dimensional form of thermal boundary layer equation becomes this in the presence of viscous dissipation, and its dimensional form then rho Cp U del T del x plus V del T del y equal to K del 2T del y2 plus mu twice del U del y square. Just its analogous dimensional form. So in the above analysis, del U del y square has been considered as the leading representative term of the viscous dissipation function. I have already explained it. So in such a case, the Nusselt number becomes function of U star, V star, X star, Y star, theta, Reynolds number, Prandtl number and Eckert number. So in absence of viscous dissipation, Nusselt number, when we will determine, it will be function of U star, V star, X star, Y star, theta, Reynolds number and Prandtl number. And in presence of viscous dissipation, it will be function of U star, V star, X star, Y star, theta, Reynolds number, Prandtl number and Eckert number. Now quickly I will give a few definitions which already you know, but we will just recapitulate it. Boundary layer thickness, we know, over a flat plate at any x is given by delta equal to 5x divided by root over Reynolds number based on x. That means u infinity into x by nu is the Rex. So root over Rex. Now displacement thickness is basically distance by which the external potential flow is displaced outwards as a consequence of decrease in velocity in boundary layer. So you can see that within the boundary layer, velocity increases from 0 slowly to the full scale velocity or the free stream velocity, which is attained at the edge of boundary layer. So there is basically, as if some fluid mass is not allowed to flow through due to viscous resistance. So this is, had there been a potential flow throughout, so how much is external potential flow would have been displaced as a consequence of decrease in velocity in the boundary layer. So that we can estimate if u is the free stream velocity outside the boundary layer, uppercase u. So uppercase u into delta star, this is 0 to infinity integration of u minus u infinity, that is the discrepancy. So from uppercase u minus lowercase u. So uppercase u minus lowercase u, this is integrated between 0 and infinity, and this integration is equivalent to u delta star. So delta star, this thickness, displacement thickness, is given by integration 0 to infinity 1 minus lowercase u by uppercase u dy. So this is the definition of displacement thickness. In the similar way, momentum thickness delta double star is defined as the loss of momentum in the boundary layer as compared with that of potential flow. So here simply we, when calculating displacement thickness, we calculated that the volume or mass by which the potential flow is as if displaced, because as a consequence of decrease in velocity in the boundary layer. Here as a consequence of decrease in velocity in the boundary layer, what is the basically momentum that is lost in the boundary layer, or rather momentum thickness, we can say that loss of momentum in the boundary layer as compared to that of the potential flow. So we can write, if we, this is a conceptual thickness so to say, but you can understand what it is. Rho uppercase u square delta double star, then it is it basically integration of u minus u infinity, that is the velocity deficit within the boundary layer, multiplied by the mass, that is rho into the local u. So u into rho into local u, that is lowercase u, uppercase u minus u infinity, this is the velocity deficit, this is the local velocity, and this is rho basically, and multiplied by area is the momentum. So rho U into flow area, that becomes the volume into rho mass, and this is the velocity. So this is the momentum, U minus U infinity. So 0 to infinity, rho lowercase u uppercase U minus lowercase u into dy. So delta double star, which is the momentum thickness, is finally given by, if we shift rho into u square on the right hand side, we can write delta double star equal to integration of u minus lowercase u by uppercase u multiplied by lowercase u by uppercase u dy, integrated between 0 and infinity. So this is the definition of momentum thickness. Now formally, we have to just talk something about laminar flow, although this difference between laminar flow and turbulent flow needs much more discussion. I will do that when we'll start turbulent flow. It is much more rigorous definition has to be given, but at the moment we can say that fluid motion, which is very well ordered, and as if one layer of fluid is sliding over another layer of fluid without getting undulated, that flow is called laminar flow. Again, I am saying this is not a complete definition. We will complement with many other attributes in course of time. Since it is introductory, I am just mentioning about it in that fashion, which is, as I said, well-ordered flow, as if fluid layers moving over another layer after layer, it is sliding over each other without getting undulated. That is the laminar flow. And turbulent flow is fluid motion, which is highly irregular, characterized by random fluctuations. And in the picture we have shown also. And for flow over a flat plate, usually when Reynolds number based on the plate length, distance from the leading edge, that is rho uppercase U into x by mu, and if at a critical distance, we will call it Reynolds number critical, and that critical distance is such that Reynolds number crosses a value of 5 into 10 to the power 5 for external flows over flat plate, or external flows in general also we can say. So, but on very convex bodies like circular cylinder, etc., these have to be again redefined. But usually flat flow and flow with mild curvature, we can say that this critical Reynolds number is 5 into 10 to the power 5, and Reynolds number is based on free stream velocity and distance from the leading edge x. So when it reaches 5 into 10 to the power 5, likely the transition from laminar flow to turbulent flow takes place. I will try to wrap up today's discussion with another very short topic. Usually we keep on saying that boundary layers are related to Prandtl number, and we have also said little earlier, then that Prandtl number is of the order of delta by delta t. Delta is the velocity boundary layer thickness, delta t is the thermal boundary layer thickness. But how? What is the mechanistic viewpoint that we can relate the velocity boundary layer and temperature boundary layer with the Prandtl number? Now let us consider a case where flow is taking place over a heated plate, boundary layers have been formed, and this is delta T thermal boundary layer and this is delta velocity boundary layer. And in this case, we have taken an example. We will take another example also. In this example, delta T is greater than delta. That means thermal boundary layer thickness is greater than velocity boundary layer thickness. We will consider, exactly the different case if it is otherwise also. But now let us consider a case when delta T is greater than delta. If it is so, then from the thermal boundary layer consideration, we can say within the thermal boundary layer, U del T del X is of the order of alpha del 2T del Y2. That means we have kept the highest convective contribution and highest diffusive contribution of thermal energy. U del T del X, highest term of the convective part, and alpha thermal diffusivity del 2T del Y2. If we again apply order of magnitude on this, and these are comparable within the thermal boundary layer. So we can say U infinity, this is delta T and this is L, proportional to alpha delta T by delta temperature divided by thermal boundary layer thickness square, delta T square. So from here we can write delta T by L square is proportional to alpha by U infinity into L. So this is very simple, just changing the side. Delta T by L square is given by alpha. This delta T is boundary layer thickness and this del T is temperature difference. So this del T temperature difference across the boundary layer. So this del T gets cancelled out. We can write delta T by L square is proportional to alpha divided by U infinity by L. So we can write delta T by L square equal to basically alpha by U infinity into L. We just rearrange. We write mu divided by U infinity into L multiplied by alpha by nu. This new term, we insert here. We have a purpose for that, but we are bringing in such a way that nu gets cancelled out. This is basically molecular diffusivity or the kinematic viscosity. We are just bringing in, multiplying it by the kinematic viscosity, dividing it by the kinematic viscosity. So from the velocity boundary layer, again we can do same order of magnitude analysis within the boundary layer. We can say that highest convective term is of the order of highest diffusive term. So U del X is of the order of nu del 2U del Y2. Here again we can substitute highest representative term of U and X. So U infinity into U infinity by L is proportional to nu U infinity by delta square. So from here we can write delta by L square. This delta is velocity boundary layer thickness. Delta by L square is nu by U infinity into L. So delta T, thermal boundary layer thickness by L square, we get an expression. Hydrodynamic boundary layer or velocity boundary layer thickness by L square, we get this expression. So now if we equate these two, we can get a very interesting situation. We'll get delta T by L square equal to delta T by L square into alpha by nu. And from here we can easily write delta by delta T square, that means velocity boundary layer by thermal boundary layer square, is of the order of basically nu by alpha. and nu by alpha is Prandtl number. So we can clearly see here delta by delta t, if we bring delta t this side, so delta by delta t squared, then it becomes of the order of nu by alpha. It is proportional to Prandtl number. So Prandtl number to the power half is order of or is proportional to delta by delta t. So when thermal boundary layer thickness is greater than velocity boundary layer thickness, then Prandtl number is related to delta by delta t in this way. That is, Prandtl number to the power half is proportional to delta by delta t. And this is a case where basically we can Prandtl number is less than 1, right? So just the other case, that means when delta is greater than delta t, we have not discussed that. I am leaving it on to you, having undergone this analysis that I have just done. Try to find out how delta by delta t will be related to Prandtl number if delta is greater than delta t. If delta is less than delta t, then delta by delta t is proportional to Prandtl number to the power half. When delta t is greater than delta, Prandtl number to the power half is proportional to delta by delta t. Thermal boundary layer thickness is greater than velocity boundary layer thickness. But when it is other way around, velocity boundary layer thickness is greater than thermal boundary layer thickness, then the relationship is Prandtl number to the power 1/3 is proportional to delta by delta t for delta greater than delta t. But this I am not deriving. I have derived the other situation. This you have to attempt. Please attempt it and you will be able to derive it. We'll stop here today. Thank you very much. Thank you for very patient hearing. Thank you.